Okay, can everybody see my screen? Yes?
Yes.
No?
Yes.
Maybe? Yeah, all right, good. Let's see. I'm almost ready. Almost ready.
Okay, Joe, so let's see you simplify this chapter.
Okay, it's very, very simple. It's really very simple, I promise. Hold on, I just want to get a couple of things straightened out here so I know what it is that I'm doing. Kind of, sort of. Let's see here. Blah, 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 blah. Contacts. Meetings, chat. I got the chat window. Hey, I'm getting good at this. I got the chat window up. All right, cool.
You are the best.
Well, thank you. Anyway, I wanted to answer a couple of questions first before we get into the chapter. So one of the questions I was asked, hold on. Here we go. That's what I want. So Catherine, how are you, Catherine? She's not talking to me. She's angry with me.
Wait, check in. How you doing?
Good. How are you?
Hanging in there.
Good. So Catherine had sent me an email, and I think somebody else sent me an email about which antenna should I get. Okay. So antennas, asking me that question, like asking, what kind of car should I buy? It depends on your needs. Okay. So I live on Long Island, and I live in Hicksville, which is right kind of towards the middle of Long Island. And, it's a fairly congested neighborhood. It's a development I live in. And I can't run, although I think I have the largest property in Hicksville, I still can't run massive amounts of antennas. So just to give you an idea, this is one of my 2-meter antennas. So this is my study. This is looking up my study window. It faces the front yard. And it's just nothing more than a mag mount antenna. And I added a little clamp. I went to Lowe's or Home Depot and I bought a $2 clamp, metal clamp. I took the plastic off of it, and I bought this Tram, T-R-A-M. I'll show you. We'll go to Amazon and look at the Tram. And this is a quarter wave antenna. It's 18.5 inches high. And it does an okay job for what I need it to do, okay? Again, I live in Hicksville. It's a congested area. I am not that far from the repeater. At most, I am 15 miles from the repeater. And again, I'm blessed that I'm a member of a club that has one of the most powerful repeater systems on the planet. So for me, this works fine. I transmit at 5 watts or 10 watts, even though my radio is capable of 50 watts, and I can hit the repeater no problem. And I spend most of my time on this repeater and maybe another repeater that's also very close by, okay? When I want to get fancy, I have, hold on, let's see here. I have this other, same window, same idea. I put a clamp, and I put this other Browning antenna, and this is a half-wave antenna with a coil. Again, 2 meters, 440, and this is the antenna that my wife uses when she's in the study, okay? So, and it's just on a clamp. It's temporary. I didn't drill any holes, didn't do anything. It comes in through the side of the window, and then we put tape on the window so in the winter it's not cold. And this withstands wind, no problem. And I think there was 60-mile-an-hour winds here over the weekend, last weekend, and these guys stayed up, no problem, okay? So these work fine, and if you want to, you can stick them on your car, all right? And but when you want to do really serious work, my wife is emergency coordinator for Aries in Oyster Bay. This is the antenna that is on my roof, okay? This is 2 meter, 440 antenna. My son and my next door neighbor, God bless them both, they went up and they put this antenna up for me, okay? And this is a full wave, 2 meter, 70 centimeter antenna. It happens to be a diamond antenna. It's a very good antenna. And there is a huge difference between this antenna and one of these guys. But this is good enough for me, okay? So The only reason that we have this huge antenna, this feeds a radio in another room, okay, in our craft room, where my wife, in case of an emergency, and there are no repeaters, the repeaters are down, and we're looking for maximum distance, we would have something like this. This antenna wasn't terribly expensive. I believe it was $99, okay? These little ones are, I think, $22 or $24. I think this one was $36. This is a little bit nicer antenna, but again, it depends on where you live and where you want to reach. Now remember, this is 2 meter 440. Okay, we're going to discuss antennas in the next 2 chapters, and I'll show you what my dipoles look like. I have very, very simple HF antennas, and they work perfectly. They work fine, and they're dirt cheap. Okay, you can make them for under $10. All right. So I hope I answered that question. I didn't want to ignore Catherine, and I believe somebody else had asked me the question as well. I didn't want to ignore the question, but I didn't want to answer the question without showing the options. So this is a tram antenna. This is a Browning antenna. They're kind of the same. And then this is a diamond antenna. And if you go to Amazon and you type in tram 2 meter, okay, they show you a whole bunch of them, okay. And again, take your pick, whichever one you like. This is the one that happens to be outside of my window, okay. The second one here, and as you can see, 531 people loved it. It's probably a lot more than that. Okay, and this works fine. It's 18 inches, 18.5 inches long. Works fine. My son has the same antenna on his car. I have the same antenna on my car. My wife has the same antenna in her car. And this is the one that's hanging out the window too.
Joe?
Yes, sir.
Yeah, just for everybody that, I know there's probably a couple of folks out there that have Baofeng. I just got, I had ordered the Baofeng accessory automobile antenna, which has a magnet on it.
Right.
And just got it back today, mail order, and put it on the roof of the car and went driving around the neighborhood and tried it out. And apparently my performance to the repeater is much improved from using the rubber duck antenna. So thank you, Phil. That's excellent. Yeah. So the rubber duck inside your car acts like a Faraday cage, which means it causes a lot of problems for the antenna to go out and in. Not that the antenna that comes with the Baofeng is not okay. It's just okay. Okay. It's on the low end of okay. And now you put it inside of a closed vehicle, you're not going to do well. This improves it dramatically. If you do buy this antenna, okay, you also need to buy, because this antenna comes with a PL259 connector on the end, you need to buy this little adapter thing here. And that's so you can use it in your Baofeng. Okay, as a matter of fact, they list it here. Okay, so you need to buy this guy here. Okay, so again, if you just go to Amazon and type in tram, T-R-A-M, 2 meter antenna, it'll bring you to the most popular trams, and they're assuming you're going to attach them to a Baofeng radio, which is what we all use in my family. Paul, you don't have any problems getting to the repeater, right? To LimeWorks repeater with what you have?
No, it works perfectly.
Yeah. So Paul lives in Hicksville as well. And she'll, my wife is always running around, and she has no problem. And as a matter of fact, she has it on her little Thunderbird convertible, and she loves it, and we have a lot of success with them. So I hope that answers that question. Okay? Any other questions on antenna? So antennas are a personal thing. It depends on your personal circumstances, is what I'm suggesting to you.
Well, definitely.
So, how far are you from the Glen Oaks repeater in miles?
Paul, what do you think? We're about 10 miles, maybe? 10, 12 miles?
From the Plainview repeater. I don't know about the Glen Oaks.
Probably about 15 miles. I'm from Wandsworth.
Maybe. Yeah, all right. So maybe 15 miles in that area, 10, 15 miles. Okay. But again, I
You
have
need
to,
In the
and this
car, you
sounds like
need this.
I'm sorry, go ahead.
But if you're inside the car, you definitely need this because it doesn't
Yeah.
work inside the car.
Yeah, inside the car, it doesn't work. You have to open the window and stick the
The
rubber
radio
ducky out the way.
Yeah, and I
So-
actually clipped the radio to the window to get it to work.
Yeah. So,
Okay,
and I have
not
yeah.
to sidetrack this, but the Plainview repeater, that's 70 centimeters, right?
right. NDMR. Yeah.
Oh, okay, thank you.
Okay.
Okay.
You're welcome. So, and again, please don't take this as bragging, but I am going to brag a little bit. We are absolutely blessed at Limemark. The head of our technical committee is just a technical genius. He really is. He runs one of the public TV stations here on Long Island, Channel 21, and everybody comes to him for knowledge and experience from a practical perspective. So he set up this repeater. This repeater is also at Long Island is as flat as a pancake, okay? And where our repeater antenna is located is the first place where it starts to get hilly and the first place that we can have semi-skyscrapers for buildings. And this is on top of one of those buildings. So we're blessed with altitude, an incredibly gifted engineer who set the whole system up, and we have top-notch equipment running that repeater. That's our flagship repeater. So again, that has a lot to do with it too, okay? So the fact that we can get away with this antenna in our particular circumstances does not guarantee that the same thing is going to happen in your location. You have to look to see how close you are to the repeater. Are you going to be using the repeater as the primary function? Maybe you're not. Maybe you're going to be like David, who lives out in Wyoming, okay, where his nearest neighbor is pretty far away. Then you can't rely on repeaters so much, and you're going to need to consider a full wave antenna. Okay? That was the question on that. And then I had a question from Phil, and Phil had asked me, and he said, hey, Joe, I have a question. If I set up an 80-meter antenna, all right? Phil, I can't remember exactly what the question was. No, you said 40-meter, right? I set up a 40-meter antenna, full wave antenna. So that's about 120 feet. Is that also going to work as a half wave antenna? And this is approximate means, okay? Approximately 120 feet. Will that work as a half wave antenna at 80 meters? The answer
Actually,
is yes.
I had it slightly differently than that. I was asking if a half wave 40 meter would function as a quarter wave 80 meter. So it was a little bit different. But
okay.
That's basically.
All right. Yeah. So he said, so it's 60 feet approximately. So a half wave antenna, will that equal a quarter wave? The answer is yes. Okay. However, and my suggestion is that you don't even bother with that so much, because the higher you go up in the meters, okay, the weaker the signals generally become. In a quarter wave 80 meter, you're right at that edge. I don't want you to get frustrated, you know. I don't know it depends also on what kind of antenna you're going to use, whether you're going to use NVIS, near vertical incident, or you're going to use a dipole, or you're going to use
Probably an inverted V dipole. That's what I was thinking about, like a 40 meter inverted V half wave, and then hopefully use it on 80 meters as well.
Yeah.
But I don't want to sidetrack the class into discussing my personal situation here. So,
Actually, it's going to be fun when we get to the antennas, but I can tell you mathematically, if you go to a quarter wave on 80 meters, it'll be down 10 dB.
Oh, wow.
Oh, yeah.
Okay.
Yeah.
All right.
And so the answer is yes, you can use it, but not, again, I don't want you guys to get frustrated and you set all stuff up and you don't hear anything and you can't talk to anybody. So not my primary way of communicating. Okay.
Thank you.
You're welcome. So
Also, Phil, I think Phil's the troublemaker of our group here. He had asked a question last class, and I told him to hold on to, trust me till we get to this part. So the question he had asked was, and maybe I misunderstood the question, but the question is, the signal leaving the antenna, is that AC or DC? And that's a hard question to answer. The answer is actually AC with a DC bias. Okay, so if we were to actually measure what kind of circuit it is with a multimeter at the antenna and Phil hits transmit, it is an AC circuit. So we have alternating current back and forth, okay? However, it's biased, it's ready for DC integration into our DC system. And that's what this is, what chapter 5 is all about, okay? And it's really very simple. They complicate this and they make things ambiguous. I don't know why, but it's really very, very simple, okay? So we're gonna do a little signal review here. If you don't remember this from your technicians, please tell me and I'll spend a little bit more time with it, okay? But I want to start again from kind of scratch. So we're going to start this way. Hold on. Let's see if I can. Okay.
And I'm sorry for being a troublemaker, Joe, but I'm heading for my extra, so bear with me.
Good for you. And you know I'm only joking. I'm only joking, of course. That's a great question.
No, I know that.
So thank you for being a good sport. And Catherine, thank you for being a good sport for all the times I called you Christine inadvertently. So I apologize. I've memorized your name. I said it 50 times.
Well, that's okay, Harry. I don't mind.
Catherine has a great sense of humor. She's made me laugh. All right, anyway. So here's the deal, all right? So hold on. Let me pull this guy up here, and we'll talk about this. So what I'm going to do is I want to talk to my friend Mark. Okay, and Mark runs his own repeater right here, okay, at 447-350, which we know is 70 centimeter, okay? Anybody have any trouble recognizing that it was 70 centimeter?
No.
Okay, good. All right, so I'm going to pick on somebody. So John Ben.
Yes.
All right, so I want to call Mark, and his call is N2, November 2, Foxtrot, Lima, Foxtrot, N2 FLF, all right? So how am I gonna call him? I'm ready to go. I'm gonna say whatever you tell me to say. Go ahead.
CQ, CQ, CQ. My call is KC2 RBI, calling N2 FLF, and then
Okay.
I say it phonetically.
Okay, great. Anybody disagree with that?
Why would he say CQ? Because he's not wanting to talk to any station. Isn't he going after a particular one?
Yeah. So excellent. Thank you. Thank you, Catherine. So yeah, so actually that's okay if we go to HF, but we normally don't use CQ when we go to repeaters. Okay, it's not considered the right protocol. Okay, all right. So we're going to try it out. Okay, so here we go, and I'm going to use my call sign, John, because I just don't remember your call sign. All right, hold on. N2FLF, Whiskey 2, Bravo Mike Papa. With a class, testing out on your repeater. Good evening, Mark. I'm just working with a group of people on their general, and I just wanted to give a little demonstration here.
Mark at 2FLF. The repeater is in Plainview, Long Island, New York. And Joe, you're coming in DFQ.
Roger that. Stand by 1 second, Mark. Hey guys, I'm going to put you on hold for 1 second, okay?
Roger that. Thanks very much, Mark. Whiskey 2 Bravo, Mike Papa. I'm clear. Have a wonderful day, my friend.
All right, take care. Regards to Seal. It's 2FLF.
Okay, so we had a nice conversation with Mark, right? Everybody agree? He's a great guy. He's my hero. All right, so I forgot. I want to tell him something. So I'm gonna hit transmit, and what you'll do is you'll see you'll see this number change, because on repeaters we transmit on one frequency and we receive on another. Ready? So we got the courtesy tone. So the repeater heard us. It's changed frequency, as you can see. I'm transmitting right now. Transmit button is on. And that was it. Also, you can see this button light up whenever I'm transmitting. Okay, watch. I'm going to transmit one more time. He didn't answer me. How come?
You didn't say anything.
Aha. Perfect. Perfect answer. Okay. So this last batch of times when I try to do something, I sent the carrier, but I sent no modulation. Okay. So no modulation, nothing happens. All he gets is some guy pressing transmit button. Okay. So the simplest form of modulation, in other words, we're adding some information to our carrier, okay, is continuous wave, or CW. It is a digital mode, right? Because there's no phone, there's no talking, and it's dots and dits and all of that stuff, okay? So what we know is that in normal conversation, one way or another, our signal consists of a bunch of different components, right? So we have the carrier, okay, right here. That's our carrier wave, blah, 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 blah. Okay, my son donated this beautiful drawing tablets for the class, but it got here too late, so I'm using my mouse instead. Okay, and then we have on either side of our signal, okay, in AM, and they're exactly the same, we have the modulation, whether it's CW or it's phone or a digital, whatever, we add this modulation. If we get rid of the modulation, we're just sending an empty carrier like we just did. Okay? The modulation, yes, go ahead.
Just to clarify my understanding of CW, it's digital because it's either on or off, right? I mean, that's basically isn't that the concept of digital,
perfect.
Right? So you read.
Exactly perfect. Exactly perfect.
Okay.
Yeah. It only has two states, on or off. Okay? Okay. So, so we have these modulation. On one side, on the upper side of what we're transmitting, and on the lower side. This is called upper sideband, right? And they're identical to each other, upper sideband and lower sideband. All right? Okay, cool. So let's assume we're using voice, right? Again, the pattern is the same. We have our carrier here. Okay, that's the power by which we push our signal, all right? And then we add modulation under the carrier frequency and above the carrier frequency, just slightly, okay? What we discovered, okay, as radio operators is we can filter out, block out one of these, and our signal would travel further. It's more efficient. We're making better use of the power. So if we transmit, let's say at 20 watts, just for argument's sake, and we could transmit, this probably can go, let's say, 300 miles, as opposed to having both of these upper and lower side bands working, we could probably only go 200 miles. I just made these numbers up, but the point is, if we just use one side of the modulation, okay, our signal will go further. All right?
You're talking about, that's called single sideband?
Yep,
So,
single sideband. That's exactly right. This form of communication is called single sideband, SSB.
Okay.
Okay? And in your study sheet, it tells you when to use the upper sideband and when to use the lower sideband when you're on HF. Okay? You also have single sideband operation in 2 meter and 70 centimeter, if you wish. Okay? Okay. Phil made a good point. All right? So anything that is, any information that uses 2 states to modulate a signal, on or off, is called a digital mode. Okay? Analog modes are things such as speech, all right, or video. Okay? So that's speech. What we're doing now is considered an analog mode. CW, RIDI, all the other things that we're going to play with in this class are considered digital. Are we
Question?
good? Yes.
Question?
Yes.
Is there any relationship between upper sideband and USB ports on a computer, or is that just a
No,
happenstance of having the same initials?
Happy coincidence. Happy coincidence. Yeah.
Thought so.
Okay. All right. So here they talk about different types of modulation. Okay. The most common and the easiest one to work with is amplitude modulation. All right. And all that means is that we're varying the intensity of the signal. So here's my plotting diagram, and our signal we send like this. And then when we talk really loud, it's like this. And when we talk soft, it looks like more like this. So we're modifying the amplitude of the wave. Okay? Hence AM. Okay? AM by definition is a carrier and 2 sidebands. We just discussed that. Get rid of one of them, it becomes a single sideband. All right? And of course, we're going to take our test, right? So we have to go by what the ARRL tells us is so, but I'll tell you what reality is in so versus what they suggest. So I think we discussed it here. Let's see. It's in here someplace. Oh, okay. Sideband operation. Below 14 megahertz, we use lower sideband. Above 14 megahertz, we use upper sideband. Okay? That's not what really happens in the real world. It's really no law that says that we have to do that. There's no regulation. It's just an agreement that somebody had at one time. Okay? So when we go to a specific band, like 40 meters, we would probably do better at, hold on. So we would do better. There's somebody on there. And notice we're in upper sideband. Okay, and the modes, you can tell the modes here. Okay, and as we tune the radio, you can hear people talking. Now, if I switch to lower sideband, does that mean nobody's on? No. Okay. The bands have gotten so busy that most people will go at their discretion. If you and I were talking and we wanted to meet on 7.150, which is a very, very popular frequency, it's a hangout, right? Everybody hangs out there. I may tell you to go lower sideband or upper sideband, depending on the circumstances.
Hey, Joe.
Anyway, yes.
On our study sheet from the technician class, it was listed as 10 megahertz, not 14.
Okay. So what I'm suggest to you is for the general under this manual, they want you to use 14.
Okay, got it.
Okay. So
actually the question's going to be, when you're at 40 megahertz, where should you be? At 10 megahertz, where should you be? All right? So it's a wide enough range that you don't need to worry about it too much. Anyway,
Okay.
let me get past this. So is everybody okay with this? Everybody is cool? Everybody understands this? All right, cool. So that's all this means, SSB. And the question's going to be on the exam is, why do you go to single sideband? Because given the same amount of power, our signal goes further. Okay? That's the answer.
Joe,
Yes.
I hate to keep disturbing you with questions, but I'm trying to
Go
visualize
ahead.
this.
I love questions. Love questions.
Hey, now you're talking about a straight AM signal, a sine wave,
Yes.
and an AM modulated signal. Could I visualize that as a wave on top of a wave, like you're looking at a sine wave, but then it has like modulations inside the sine wave that would make the sine, like say on an oscilloscope, if you were looking at it on an
Yeah.
oscilloscope.
Yeah. That's a great
Like
question.
any waves on top of the main sine wave, is that what the sideband thing is?
Yes. Think of it as, let's see if I can get this pen to work, okay? So this is our signal, right? And now what we're going to do is we're really going to zoom into the signal, okay? And I'm going to try to emulate that. Maybe not. Okay, if I were to zoom in to this little section right here, right? Ooh, I did strange things to my pen. Okay, we're going to zoom in to that little section, right, where it meets this. And we've amplified this a gazillion times, right? And here, it's coming down here. What's really happening is there's another section here and another one here. Okay? So this wavelength, instead of being like this, right, is actually looks like, I can't believe the mess I just made. All right, let's see if I can do this. It actually,
So it's
wait a minute. It
like
looks
the
like,
band you're talking about.
yeah, so the thickness of the line, I'm gonna try to do this. So the thickness of the line, this is what it actually looks like, okay? And where that lower sideband and upper sideband lives lives here, lower sideband lives here.
Okay, that makes it a lot easier.
Okay.
I'm a visual kind of guy, so thank you very much.
No problem. All right, good. And I love the questions. Keep them coming, okay? So that's one way to do it, okay? And again, depending on what you're using, whether you're using CW or phone or digital, that space, the thickness of the line varies. So this is perhaps phone, and then if this works, it's slightly thinner. Let's see if I can make it go thinner. Ew. Anyway, the thickness changes. So this space that it occupies, it's the bandwidth, okay? How thick this line is the bandwidth. So phone takes up a ton of bandwidth compared to CW, where the line is much thinner, okay? And if we had video, it would be double this, or triple this, actually. It would be huge, all right? So the line would be really thick, and it would take up a lot of bandwidth, okay? Does that help visualize what we're discussing?
Absolutely.
All right, cool. Yeah, so the thicker the line, the more the bandwidth. I'm okay with that because that's exactly what it is, okay? Okay, so cool. So we have AM. We got AM under control. No problem, okay? But now, of course, we have to make things fancy, okay? And we can also add other things to it. And we can change in a frequency modulation model, okay, FM radio, what we're really doing, instead of, oh, that's way too thick. Okay, in an FM model, instead of adjusting the height of the wave, okay, and then making it softer, whatever we're going to do, in FM, what we're doing is we're adjusting how close the waves are together.
and then we can make them very close together. And in the same amplitude, we can make them further apart. We're adjusting the frequency, how many times per second that wave goes through its cycle. That's FM, okay? It's a more stable signal, and it's a little harder to decode the modulation or the information within that signal, okay? However, the quality of the signal, of the audio, what you perceive as the audio, is superior. That's why AM, it's good for a news broadcast station, but everybody in their car, when you want to listen to music, you turn on FM, okay? It gives you more latitude in the signal adjustment. Things just sound a little nicer, a little smoother, okay? You can also adjust the phase, which I don't want to get into, and they shouldn't really even be discussing this at this point. We can adjust the phase of the signal. Does everybody understand the concept of phase?
No.
Cool. I knew you didn't, so I knew Catherine was ready to volunteer because she's a good sport and she makes me laugh. Catherine.
Yes, sir.
Okay. You know row, row, row your boat, right?
I do.
Okay. Would you be kind enough to sing one verse of that for us, please?
Row, row, row your boat gently down the stream. Merrily, 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 life is but a phase angle.
No, not a phase angle. Okay. So here's Catherine, okay? And Catherine, row, row, row your boat gently down the stream. Merrily, 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 life is but a phase angle, okay? All right, cool. She's perfectly in phase. It sounds great, doesn't it? Doesn't she have a beautiful voice? Really sounded good, okay?
It does, absolutely. Yes.
I'm telling you, just the best. John Seymour, I haven't picked on you like all night. You with me, John?
Yeah, I'm here.
Okay, good. So you guys, Catherine, John, you're going to sing this in the round. So Catherine, you're going to start when I say go, Catherine. And John, you're going to sing one chorus of row, row, row your boat when I say, John, go. Everybody got it? All right?
I think so.
Catherine, go.
Row, row, row your boat.
John, go.
Row, row, row your boat gently down the stream. Merrily, 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 life is but a dream.
Okay. A little bit more complicated to find out who is doing what, okay? And John was 90 degrees out of phase from Catherine, all right? So what happened here is Catherine started singing, okay? I'm going to make this a little thicker so where it's a little easier to see, okay? So Catherine started singing, row, row, row your boat gently down the stream. When she hit this point, John came in, okay? And he started going, row, row, row your boat gently. And then Catherine kept going. So the phase angle looked like this. So John was 90 degrees out of phase. I'm sorry, 180 degrees out of phase from Catherine. I don't know why I said 90. It's 180 degrees out of phase with Catherine. Okay? So as Catherine was approaching this zero line on the x-axis, John was coming in. All right? That's called being out of phase. Okay? Twice as much information, right? Because we heard Catherine, we heard John, but a little bit more complicated to decipher who was doing what. All right? And your radio has to do that work. So in essence, when we talk about breaking down the signal, our radios, whether it's the car radio or an amateur radio or a 50 gazillion watt, most powerful TV station, whatever, okay, they have to discriminate between these signals that are out of phase. And they can isolate John and they can isolate Christine. And you'll see how that's done. Okay? But anyway, that technique is called phase modulation. And we vary the phase angle. Okay? Actually, it gets even a little bit more complicated than this, but I am not going to go into that for this class.
Hey, Joe, can that whole phase thing kind of be related? I was an audio engineer at one point, and if you had plugged in your speakers and swapped the red and black wiring, You would cancel out your base signal because they were 180 degrees out of phase.
Exactly correct. Exactly the correct principle. So what was being discussed here is when you hook up the speakers to your car or in your house, there's a positive and a negative, okay? And sometimes if you didn't follow it exactly, what would happen is, I'm sorry, who is my audio engineer?
John Seymour.
Hey, John. So, John, I'm sorry, John. I don't want to refer to it as "Hey you." I want to know who I'm talking to.
No worries.
So exactly as John said, if we accidentally reverse the leads, okay, on older amplifiers, it would cancel out the bass. It would sound thin, okay? So normally amplifiers made in the 70s and the 80s, kind of, and depending on whose it was, you had to be careful how you wired them, okay? On high-end stereo, Bose, Macintosh, that kind, you still have to do that to a certain extent, but now they have a circuit that automatically corrects for it. How cool is that? Okay, and we're going to discuss
that's constructive interference versus destructive interference.
It's not really interference. It's called a feedback circuit. It's not really interference. It's not really interfering with anything. It just sounds kind of crummy. So that's a good question. I don't know what to call it. I don't know. It's above my pay grade. Okay, so I don't know. But anyway, so that's what phasing is. All right. So
as a boater, as a boater, I've been watching these programs about rogue waves, and they talk about waves that come together on the ocean that are in phase versus out of phase, and when they're in phase, their height can actually double.
Oh, baby, you got it. You got it. I'm an ex-boater. Okay, I just ran out of money, so I'm an ex-boater. Okay, and that's exactly right. That's exactly correct. So in the ocean, okay, the waves that hit against the beach and against your boat are either in phase or out of phase. If they're in phase, watch out. That's what they call those rogue waves that you hear about that are twice the height of a regular wave. Those rogue waves are, they're serious. They're serious. They can ruin your whole day. Okay. All right. Anyway, so that's what modulation, that's what phasing is for our purposes. Okay. I'm not going to get into this whole heavy-duty definition of phasing. That's all you need to know for right now. It gets a little bit more complicated, but we still have 3 chapters to go. Okay, bandwidth, we just discussed. That's the thickness of the line, right? And then they talk about what each individual mode uses as far as bandwidth, the thickness of the line, right? So CW, hold on. CW, very thin line, no problem. Okay, that's this guy here. That's this guy here. Okay. Phone, much thicker line. Okay. And then as you go to different things, it gets thicker or thinner, and this is how much bandwidth you use. What's important for you to know for the exam is that CW, continuous wave, uses 100 to 300 hertz, not kilohertz, just hertz. Okay? Not thousands of hertz, just regular, ordinary hertz. It's tiny. Okay? If it was up to the FCC, they would have everybody never use phone, only use CW. Why? Because you can pack in a lot more people in CW than you can in phone. All right? So that's what bandwidth means. All right? And they go into this whole big technical hoopla, and it's not necessary. Okay. Any questions? We good so far? Yes?
Yes.
Okay. Yes. No questions? Good. All right. So we're going to talk about, we're going to build our own radio. All right? So we're on Gilligan's Island and we're stuck. And we want to get off the island. Right? So how are we going to do that? Okay. Very simple. What we need is 4 basic things in a radio, okay? We need an oscillator of some kind, and I'll define all of these things, a mixer, multiplier, and modulator. Those are the four things theoretically that we need. All right? An oscillator, by definition, is something that consistently, for our definition, is something that goes back and forth at a regular interval. So the pendulum on this clock is an example of oscillation. All right? What makes it oscillation, all right, is the fact that it spins exactly the same distance this way and this way the first time it swings, as opposed to the 50 millionth time that it swings. It's the same distance. That oscillation is consistent. That's what makes it an oscillator. Okay? So if you think of that principle, electronics works exactly in the same way. Okay? So, there's different types of oscillators. And oscillators will define what frequency we're on. Okay? Whether we're on this frequency, or we decide to go to this frequency, or we decide to go to this frequency, it's an oscillator of some type.
That's the carrier, right?
Well, that's everything. Right now it's the carrier. If I switch to FM mode over here, right? Let's switch to switch to FM mode. Okay. In this mode, this is the carrier, and slightly underneath it, 400 hertz underneath it is lower sideband, and 400 hertz above it is upper sideband. So this is, you're right, this is the carrier, and associated with it, okay, because I'm in voice mode. I'm sorry, 600 hertz. 600 hertz below it, 600 hertz above it is the modulation. If I'm talking voice. If I'm going CW mode, okay, it's the same frequency. It shouldn't have changed. It's the same frequency, but I'm only going to use 150 hertz above this or below this, depending on which one you want to use. So 150 hertz is here. Okay. This is kilohertz, megahertz. This is regular hertz. So as you can see, it's very tiny. So I would go from here to here. All right. Anyway, so the oscillator is what's going to decide what band I'm on, what frequency I'm on. I'm sorry, what frequency I'm on. So the oscillator will decide that I want to go here, I want to go here, wherever I want to go. I want to go here, okay? And there's different types of oscillators which we'll discuss. So that's component number one that you need, okay? So you need something to decide what frequency you're going to be on, okay? All right, cool. What creates an oscillator? All right. Oscillators are created in three different ways. The single most accurate way for an oscillator to work is a crystal oscillator. It's a piece of quartz cut to incredible precision, like a diamond, literally like a minute diamond. And it's cut in such a way that when you pass electrons through it, it vibrates at a consistent rate. Okay? That crystal will produce a specific frequency. In the early days of amateur radio, that's exactly, forget amateur radio, of radio, that's the way it worked. Okay? So if you wanted to work this frequency, 24.923, you had to go to Radio Shack and buy a 29.923 crystal. You'd have to order it. They would make it for you. You'd wait 2 weeks, and you'd come back, and you plugged it into your radio. And your radio, if you were lucky, had 6 slots or 12 slots to put in crystals. If you wanted to work here on this frequency, you would have to go out and buy another crystal. Okay? That's the way it worked. But it is by far the single most accurate way of getting onto a frequency. No question. Okay? But it's PITA, right? Painting a butt to work it this way. It's to make you crazy, right? So they came up with variable frequency oscillators. Hey, that's our tuning knob, right? VFO, that's this guy. So that when I adjust this, I can go back and forth like this. Hey, I remember that. Variable frequency oscillators
And there's two types of them, okay? They're made of RC, resistor, capacitor, and they're made of LC, inductor capacitors, okay? And they vary slightly as how they work, but they both work very, very well. So using resistors and capacitors, we can create this VFO, and if we use inductors and capacitors, why isn't my thing working? Hold on. God, I hate this program. Anyway, come on, wake up. Here we go. We're moving now. All right, here we go. Hold on. Sorry, folks. So, come on, any day now. All right. So, using, all right, here we go. So using inductors and capacitors, or resistors and capacitors, or the combination of both, I'm allowed this VFO type of thing, where I can adjust the frequency however, in whatever increments I want. Okay? All right, cool. That's all, all of this means. Go ahead.
So in an RC circuit, would you use a variable resistor or a variable capacitor, or doesn't it matter? It just depends.
It absolutely matters. It depends on the rest of the circuits around it, depending on what you want to do. Okay? Depending on what you want to do. And well, hold on to that question, Phil. Okay? That's another thing. You're like 4 questions ahead of me. Hold on to that question. Okay? So, so the variable frequency oscillator is normally done with inductors and capacitors, okay? But not always. It depends on what we want to do with it, all right? And then they added this thing called phase lock looping and direct digital synthesizers. When we discuss software-defined radios, which we'll play with, we use this direct digital synthesizer. What does that mean? That means our computer. This is not a software-defined radio that we're playing with at the moment. So this is a robotic function, but it looks just like this. Our computer becomes the tuner, the variable frequency oscillator, and we will digitally synthesize the frequencies. Okay? Again, nothing as good as quartz crystals. Then after that, you can use inductor capacitor, very good, resistor capacitor, and then almost as good, not exactly the same, direct digital synthesizer. Guitar players, here's the scoop. You can get a modeling amp. You can get a modeling amp to emulate a Fender Pro amp from 1950, and it's almost maybe 97% as good. But you plug it into a 50s Fender Pro amp with tubes, you can tell the difference. Okay?
Man, if you have an ear for that, you should be a professional producer.
You'd be surprised. You'd be surprised. You start playing an instrument, especially an instrument that's amplified like guitar or bass, okay? You know what? For the longest time, I couldn't hear the difference. And then one day, you can definitely hear the difference.
You can definitely
hear
the
maybe
difference.
Your audience can't hear the difference, but then you can hear the difference, and then you don't play quite as good. Guitar players, do you disagree?
Agree 100%.
Yeah.
Oh, it just takes a very discriminating ear, and I guess my age has really affected my ear, so it's harder to have an
you know, stand in front of an amp 20 hours a day, that'll affect your hearing too. No, it just feels better. It just feels better.
That's exactly what I did. That's the problem.
No, I can hear it between when Joe fires up a tube amp and a non-tube.
Yeah.
And then I'm tone deaf, but I can still.
Yeah. So anyway, so direct digital synthesizers, they sound a little bit different. That's the point. And you'll be able to hear them, especially if you get into software-defined radio. They're excellent. I'm not putting them down. I'm just letting you know that it sounds different. Nothing sounds as good as a crystal oscillator. Okay. All right. Let's talk about mixers. When I was studying electronics and radio, this was the hardest thing for me to understand. What the hell is a mixer? What does it do? And they don't really explain this to you, okay?
and this whole thing of heterodyning and blah, 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 and all of that. It's super simple. They make this so complicated, okay? Anybody here drink mixed drinks?
Yes.
Okay, what's your,
Never.
I already talked to John. Let's talk to David. Do you drink? You drink mixed
Yes.
drinks?
No.
Mixed drinks.
No.
Okay, who drinks mixed drinks?
John Ben.
Hey, I'm sorry, John Ben? All right,
Yes.
John, what's your favorite drink?
How about a Manhattan?
Okay, can you tell me, I don't drink, which is, by the way, not something I recommend, okay? So I do not drink. We're a mistake in my life, all right? So we're going to mix a Manhattan for John Ben, okay? John, what goes into the Manhattan?
Bourbon.
Bourbon. So we got bourbon. So we're going to pop that puppy in there. What else?
Little sweet vermouth.
Vermouth, right? And we're going to throw that sucker in there, right?
And a dash of bitters.
Bitters. And I'm just going to abbreviate that BIT.
Yeah.
All right? All right, and we're going to throw that sucker in there, right? And then you put it in a container of some kind, right? You put the lid on it, and you like it
Ice.
shaken or stirred?
Shaken.
Shaken, all right. So then we're going to shake this sucker up and down, whatever, okay. And this vessel that we made this Manhattan in, what's that called?
Shaker.
A mixer.
A mixer. That's what it's called. It's called a mixer, okay? Guess what? You now understand what a mixer's function is, okay? Exactly the same thing, all right? So what it does is it takes everything in the spectrum and allows you to break it down. So a Manhattan tastes different than just straight bourbon. Is that correct, John? John Ben?
Definitely.
All right.
Definitely.
Yeah. So bourbon, even though it's a component, the Manhattan tastes different than just bourbon or just vermouth, right? If you drink vermouth, you're not drinking a Manhattan. And certainly if you hit the bitters, you're certainly not drinking a Manhattan.
Right.
So the combination of all of them is what makes a Manhattan the perfect Manhattan. Same type of deal here, okay? So what a mixer does, okay, is it takes all the signals in a specific band, and I'm picking on 20 meters here because this is where I happen to be, okay? And the mixer allows us to break this entire band down, okay, into its component parts, right? So it takes this whole band, okay, and allows us to differentiate exactly as Phil said. There's the carrier, all right? And then we have lower sideband and upper sideband, and we're able to differentiate all of this stuff. What band we're on, is it upper band, lower band, the carrier, it gets all of that. So it's a mixer in reverse. It's John's container in reverse. So it starts off with the Manhattan, and it's able to shift out the bourbon, the vermouth, and the bitters. Yes? Good? We clear?
Yes.
That's it. That's as hard as it gets, okay? Not really so complicated, okay? And then they go into this whole thing, how it measures the sum and the difference and blah, 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 and that's great, okay? But it's not really that important, okay? Frequency 1 and frequency 2, that relates to the carrier, whether it's upper band, lower band, blah, 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 blah. Not so important, okay? All right. What we do is we take it one step further, all right? Because this is such a wide range, okay? We're using the tuning knob to tune between frequencies, right? And this function is a local oscillator. What does that mean? That means I can locally, without doing anything else, tune to a specific frequency. Great. Now what the mixer does is once I arrive at a frequency of my choice, it then splits up this signal, whatever signal I'm on, into carrier, upper, lower, et cetera, et cetera, et cetera. Everybody understand? All right, so that's what we talked. Yes, go ahead.
That through the reverse and the transmit function, or is
transmit's a little bit more complicated.
okay? Sorry.
So I don't know. You know what? I've never really considered that remark. I I won't comment on it because I haven't considered it. I think transmitting is a little bit. Is it the reverse of transmitting? Yeah, maybe. Yeah. If it's not, it's very close. Yes, I would say yes.
Thank you.
All right. Multipliers. Okay. Multiplier is very similar to a mixer. Okay. But what it does is it filters out harmonics of a specific signal. All right. So anytime we have a signal of any kind, it doesn't matter. Every wave works exactly the same way. I'm going to send you for the weekend, I'm going to send you this great video, the coolest video on waves you have ever seen. It's from the 1950s. There has never been a better video to beat it. And it discusses wave motion, okay? And it pertains to waves in the ocean, waves in sound, any kind of wave, okay? So any wave that's produced, any wave, okay? Doesn't matter if it's radio, water, makes no difference, okay? The wave looks like this. And it would be great, or maybe not so great, if this is all there was, okay? But that's not what really happens in nature. This wave is accompanied by a companion wave called a harmonic wave, normally at some interval of the original wave, and that's considered the harmonic wave, usually in divisions. So it could be a half wave harmonic, could be quarter wave, blah, blah, blah. So every wave constructed by nature has a harmonic to it, okay, above and below the original wave. What the multiplier does is it cleans up that harmonic. It cleans up that harmonic wave and makes the original wave just shine through. That's important on 2 meter and 70 centimeter. Okay? Why? Because the waves are so close together. If we didn't have a multiplier, it would be hard for us to understand the modulation that's coming through. So it becomes very important in 2 meter and 70 centimeter. It's important in all the bands, but especially in UHF, VHF, and they make a note of it here. Okay? So all this means is that it's going to try to tune out, okay, the harmonics so you can hear it better. That's all it means. Okay? Modulators, you guys have any questions, stop me, okay? Modulators, all that they do is they take whatever we're doing, whether we're talking or we're sending digital, it turns it into some kind of form that we can attach to the wave and sends it out in the air. When we receive, okay, we have a demodulator, and it takes that signal and breaks it down into components, parts, okay, and sends it over to our amplifier. That's all it is, okay? Okay, amplitude modulators, again, works just like a regular modulator, only we're working with the height of the wave. All right, and that's it. And so they discuss the different types of carriers and waves and single sideband. Very simple. Don't let any of this stuff throw you off, okay? All right, and that's all I want you to know for here. That's all that's really important. All right, and they talk about how close is too close. All right, that's a good one. What they are very concerned about, and they will ask you a question on, okay, is, everybody can see this, right? So we're on a, I'm going to take this, I'm going to go up here so it's easier to see, okay? Because it's just our nature, because, you know, I think it's a toss-up between Phil and my son being troublemakers. They're going to go here to the very edge of the band, all right? And then, no, they're not. I'm only kidding. I'm picking on them because they have good senses of humor. We're gonna
Not at all. I love it. I know I'm a troublemaker, Joe. I apologize.
It keeps you young. Anyway, so we're going to go to the edge of the band, and we're going to start transmitting phone. What they don't want you to do is to fall off the edge of the world. Okay, so the world is flat, and if you go one too many, you end up in hell, okay? So you don't want to exceed that band edge. and they're going to ask you the question in such a way as they'll test two different concepts, all right? So they're going to say to you, you're at the band edge, you're right here, okay? You're at 24.988, okay? Can you use phone? Okay, and then you're going to have to go back to your study sheet, see how much phone uses, but of course you don't have the study sheet for your exam, okay? And you're going to have to figure out, let me see if I can switch to this, all right? And you're going to have to figure out how much that particular mode uses and see if it puts you over the band edge. I think it's in here someplace. Wherever I have it. Ones I want you to know are here someplace. And speed.
There.
Yes, did I pass it? Oh, here we go.
Channel
So-
separation.
Yes, channel separation. So know these. Single sideband uses 3 kilohertz. Okay? So if we're close to and they'll give you a specific band, and you're right here, 3 kilohertz would put you over the band edge. So that's an illegal transmission. All right? So the ones I want you to know are CW, 150 to 500 hertz. I said it 15 times. I'll say it 3 more times. Hertz, not kilohertz. Okay? So this is tiny. So the question they're going to ask you is about single sideband. All right? So we want to fall off the band edge, and that's all this means. All right? So if we move this over, we fall off the band edge, we're doing a no-no. Okay? All right, they're very big on that. Okay? Frequency and phase modulators, again, we can control phase modulation, so we can control where in the signal path we have the modulation entered, so we can send more information. What does that mean? I sound really technical. I don't mean to. I'm sorry. So we can send signals like this: row, row, row your boat gently down the stream. And then John comes in: row, row, row your boat gently down the stream. We can send signals this way. We can adjust the phase modulation and send twice as much information. But we use up more bandwidth. That's all this means. Okay? All right, blah, 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 blah. Okay, transmitters. Okay, transmitters, a little bit more complicated, okay? The simplest transmitter you can use is CW. Very simple, okay? So all you need is an oscillator, something to pick a frequency, whether it's a crystal or it's a variable frequency oscillator. That's it. A keyer, some kind of amplifier, and a really kick-butt antenna. That's all you need to send CW, okay? Technically, electronically,
double, triple, check.
somebody needs to mute their phone.
Hold on.
And I think it's David. Yeah, thank you, David. So, electronically, we can do this, okay? If you have, for example, a 110, I don't recommend this. I do not recommend this. Do not do this, okay? If you were to plug in an extension, well, first you cut off the end of the extension cord and you bare the wires that you're going to plug into the wall. You plug it into the wall. If you're brave enough, actually stupid enough, to touch those two wires together, okay, you could actually create a spark, and it's self-amplifying, and the wire would act as an antenna. You could pick this up, theoretically, as a type of CW. You could send CW this way. It's actually very simple to do this. You don't need a fancy amplifier or anything. As a matter of fact, during World War II, they could make these out of almost nothing, okay? You needed a pencil, a foxhole radio. Anybody familiar with foxhole radios? Okay. You needed a razor blade, the tip of a pencil, and a safety pin. And you could actually make a little tiny transmitter and receiver. Okay, anyway. So, so you need all of these components. Now when we get to something a little bit more complicated, we want a little bit more power. We have this oscillator, okay? We have a mixer. We're talking about transmitters now. So the mixer is now working like John's mixer. We're putting the individual components in, right? Here and here. And it was running through the mixer and then out the amplifier. This filter, the product detector, it's called, it will tell us what kind of signal it is. And that's what I mean when I answered the question. The circuit that leaves the antenna is AC, but DC biased. Okay? This is a DC structure. What this means is that it will decide whether we're going out via phone, whether we're going out digital, whether we're going out CW, and that's called the product detector. Okay? Sometimes we use split frequency. We listen on one channel and we transmit on another. Our repeaters are like that. That's an example of that. And more importantly, if you're going to chase the International Space Station, you receive on 2 meters, you transmit on 70 centimeters. Most radios, even the cheapy Baofungs, have the split frequency operation capacity. Okay? And it's very, very common to use that when you're trying to talk to long distance stations. All right. Okay, phone transmitters. So we're voice, again, same thing. We start with something that decides the frequency. We use this device called a balanced modulator, okay, and a speech amp. What these things do is prevent overmodulation like this. So they'll prevent overmodulation, spare us signals, put into this filter, which could also be a product detector, mix it all together, kind of another filter to clean it up, out through a linear amplifier, which just amplifies the signal, and out through the antenna. Okay.
Was that an intentional object lesson?
Yes, it was. Absolutely intentional.
Okay.
Okay. All right. So we're going to get into an area that I know very little about, which is linear amplifiers. I don't believe in amplifiers. Are we up to? All right. Anyway, we're going to get to it before the end of this chapter. Linear amplifiers. I own many things when it comes to amateur radio. My son's in the class. He'll test to that. One thing none of us own is an amplifier. Okay. So I'm not saying they're bad. I'm not saying you shouldn't buy one. I'm just saying we don't own any. Okay. Anyway. All right. So the FCC does not specify the bandwidth limits on any phone signal, except to say that signals should not occupy more bandwidth than is dictated by good amateur practice. So the question is going to be on the exam, how much power should you use to get your phone signal through? Answer, the minimum amount of power necessary. This is not the minimum amount of power necessary. Okay? This gentleman has family on Saturn. He must speak to them, okay, on a regular basis. These are very high capacity. These guys here are very high capacity amplifiers, and he has 1, 2, 3, 4, 5, 6 of them, okay? Each capable of increasing it. Well, that's not true. Each one of them is 1,500 watts, but you can add them, stack them together. 15, 3,000, 3,000, 45, 6,000, about 10,000 watts in this room, okay? 10,000 watts is your basic FM radio station or AM radio station.
But look how happy he is.
I know. You know what? And I have to tell you, can you hear the meowing on my part? I am just so jealous. I really am. What can I tell you? But anyway, so please make note of the question. Yes, go ahead, sir.
Troublemaker here.
Yeah.
What does bandwidth have to do with power?
Okay. As you increase the power, as the power increases, the amount of bandwidth you take will increase because you're creating spurious signals. Your harmonics increase, okay? As remember, we're on AM, right? So our amplitude is going to increase. So as we start adding more power, okay, the only way the amplitude, so this is a normal signal like you and I would produce. When we put it through an amp, okay, the signal looks like this. The amplitude increases dramatically, okay?
Okay,
So-
but I thought bandwidth was the thickness of the waveform, and not
Yes,
necessarily.
and that's exactly correct. And that's exactly correct. But as the amplitude of this increases, we're also creating spur signals. The harmonics start to get very large. And since it's a
Okay.
more powerful signals, those harmonics quadruple over the original signal. Those things become like this. I mean, they become huge. Okay?
Okay.
And the other problem is, there's different types of amplifiers. Depending on the amplification that you use, it can either be okay or not okay. Okay? Depends on whether you bought it, who you bought it from on eBay, basically. Okay? And you gotta be careful with that stuff. All right? So, they talk about this model too. These are low frequency transmitters. Speech amplifiers, and I'll show it to you here in this particular, we use the speech processor, which is this guy. I don't know if you, it's hard for you to see. So right here, the speech processor, this guy here, all right, and this is adjustable. And what that does is it cleans up my outgoing signal, So it gets rid of the S and the S's. It makes everything a little bit clearer and a little bit, not too loud, not too soft, just about right. If I crank this up a little bit too much, you'll get this kind of sound. Like the CBs, where the guy goes, and then the guy's talking to you for 15 minutes. You have no idea what he said. That's because there's no speech processing in CBs. Amateur radio, most radios have speech processors. They'll avoid that. Okay? It's just a circuit that helps you get past that. Okay? All right, cool. They tell you about the maximum deviation. Deviation is how much your radio can be off. If you're on a specific frequency, what's the maximum your radio can be off? The answer is 5 kilohertz. It's impossible for you really to know that except if you transmit an awful lot, all right? And people say you should be on a specific frequency, like here, and they tell you, well, I'm not hearing you here. I have to tune in, to this. From 350 to 355. I hear you better on 355. Well, if that's the case, then you've reached maximum deviation, all right? And you have to take your radio in to be fixed. Okay? All right. The point that they're trying to make through all of this is be careful. Don't go over the band edge. Very, very important. Okay? And if you don't hear people exactly correct on your frequency, it's because there's some kind of overmodulation, deviation, spur signal, too much power. Okay? I know you're all 100% honest. I know you will never exceed the 50-watt limit on 2 meters. I know you will never exceed the 1500-watt, but you never know. Somebody comes along and gives you an amplifier, blah, blah, blah. All right, anyway. And that's what we talk about, harmonics and spurs. These are signals that occur when this gentleman comes in and he tunes in his radio. I happen to know who this guy is personally, okay? He comes on 40 meters, that's it. Have a nice day. Okay? If he's not in a good mood and he cranks it up, he's really a very nice guy. But he likes to get his signal across. And if he wants to talk to Australia that particular night, this gentleman happens to live in Louisiana, and he wants to talk to Australia that night, okay? That's what's going to happen. He's going to talk to Australia. And you'll hear his harmonic signals, a whole bunch down the band, okay? It could be, 10,000 kilohertz over. And it's just crazy. Overmodulation, we just discussed that, okay? Where we send too much modulation,
and the signal becomes distorted, and the shape of the wave changes a little bit. The height certainly changes, and you get all these harmonics in there. Okay. Okay, and one way we can do it, we can adjust as we have cutoff filters that we can use to avoid overmodulation. We can use these cutoff filters down here, and we use digital signal processing to clean up the signal. Let's switch over to, let's see if I can find somebody. All right, so that's what it sounds like. I put the noise, you can just hear the noise in the back. You can hear somebody talking in the background. I'm going to turn on digital noise reduction. And then noise blanketing. And I can adjust it here. And it's tough over the phone to hear what's going on. This one you can hear a little bit better. And then playing with these, you can pick up the really distant signals, okay? It takes a lot of practice. It takes a lot of patience, where you can use these filters to your best advantage and pick up the weak signals. So after a while, the fun part of this is talking to some guy in the South Pole, okay, or near the South Pole, and you're going to have to play with these filters to make that happen, okay? That's the bad of it, you know, bad news of it. Okay, automatic level control, it comes standard on all of the radios and on all of the HF radios. And what you can do on the HF, now this is a type of speech processor and gain. And what they'll do is, as soon as you start over modulating, because we have a tendency to get louder the harder we try to communicate with somebody, okay? So it's the old joke, you know, person walks in and everybody's talking French, and he says, "Hi, my name is Joe," and they're all looking at him and talking to him in French. So what his response is, "Hi, my name is Joe." Like, that's going to make a difference, okay? But it's just human nature to do that, okay? So the ALC prevents, the automatic level control prevents that overmodulation. That's what that does. Question on the test. Definitely. Write this one down. It's going to be there. This two-tone test, okay? It's how we test a transmitter to make sure that it's working correctly, that your signal is clean. And what you need to know about the two-tone test, it's on your study sheet, is that it's two frequencies not harmonically related. So for example, they take a 700 and the 1900 hertz signal, and that's how they test your transmitter. They send out a signal on 700 hertz and 1900 hertz, and they measure it with an oscilloscope. Okay? All right. CW, we just talked about it. Speech processing, we just talked about. And basically, it's just a filter that improves intelligibility of the signal under poor conditions. Okay?
Joe,
Yes.
I don't mean to divert this, but you were just
Absolutely,
talking
and keep it coming. I'm ready.
you were just talking about two frequencies that I understand to be in the audio frequencies, 700 hertz. So how does that become? I thought radio frequencies were considerably higher than that.
Well, they are. They are and they aren't. I can go radio frequencies down to 1 hertz. I can send out a signal at any hertz level that I wish. They pick the 700 and 1900 hertz as typical frequencies, and we generate them through your transmitter. So what we do is, instead of connecting up, think of it this way: we have a magic box, and that happens too, and it's really called a tone generator. Okay, and we can set it to anything we like. Okay, and we can send it to 700 hertz, and we can send it to 1900 hertz. We would then transmit, hit the transmit button, hold this box with the speaker next to your microphone. We would transmit at 700 hertz and 1900 hertz, an audio signal. So it's just a tone. And we would see what comes out the other side. and we would
Okay.
measure it with an oscilloscope. If the variance is plus or minus 5%, there's an issue. So your modulator isn't working correctly, your mixer isn't working correctly, something is not working correctly in your transmitter.
I
Does
see.
that
So
make
that's
more sense? Yeah, make
standard.
more sense? Yeah. Okay. Yeah, it's a little bit confusing. Okay. So we talked about speech processors, blah, 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 blah. Okay, and it just smooths the signal out. We use a technique known as compression. Again, I hate to pick on the guitar players, but the guitar players know this more than probably any other instrument, right? So guitar players, we have a compression pedal, right? Everybody's used one at
Mhm.
some point,
Yep.
except for the acoustic guys, okay? So if you're an electric guitar player, there's a compression pedal. And what that does, it smooths it out. Ever hear a guitar with that really smooth, really sexy kind of sound, that's compression. It's that kind of, everything sounds like it's just running together. That's,
It flattens out the waveform.
Actually, it just compresses everything. It puts everything in an envelope that makes it more comfortable for us to hear. Okay. And our perception of that is, in this particular case, it can sound actually louder than the signal is through an acoustic trick because it's deceiving our ears. Okay? It's a kind of like a visual effect, but for your ears. Okay? You got to be careful. Don't overprocess. Okay? Because if you do, it'll sound like mud. But don't worry, they'll tell you it's sounding terrible. Okay. Overmodulated, keep adding power, you'll absolutely overmodulate and overdeviate, okay? So, as I explained to you before, the increased strength of either FM or AM, much more prevalent on AM signals, okay? As we add more power, it starts to distort the signal because of the basic of amplifiers, okay? There is no amplifier ever made, audio, radio, no amplifier that will give you zero distortion. Not possible. Okay? I don't care how much money you spend on an amplifier, it will distort the original signal to some extent. If you keep adding power, that distortion increases geometrically, not arithmetically. Okay? So it doesn't take a lot of power before the signal really gets distorted. Also, if you're having problems with your product detector, when you send out CW, it isn't a clear dit and dot, okay? You'll hear like a switch opening and closing. You'll hear this big clicking, clunking sound. So you can address that too. Amplifiers. All right. I don't own any. I am not an expert on this, okay? And the reason is because it's just not fun for me, okay? And they use a lot of power. And in case of an emergency, I want to know how far I can reach without an amplifier, how far I can reach with just my battery, okay? Amplifiers don't run on batteries for the most part, okay? All right, cool. So they start with Class A, okay? They're the most linear. They have the lowest signal distortion. They are expensive, okay? You can turn them on and leave them on all the time, but the amount of usable gain in dB is limited. So you get an amplifier, if you get 10 dB maximum downhill with the wind on a sunny day, that's a lot, okay? And usually you turn them on, you leave them on. But 10 dB is a lot, and some people like to have. Of course, we're talking about legal limits, okay? All right. You'll notice that the question here is in blue. So that's a good indicator that it might be on your test. And the question will be, Class A amplifiers offer the lowest signal distortion. Okay. Class B, one level down, it has good linearity, which means it works pretty well over a wide variety of circumstances. You have to be careful with design and adjustment. They're much cheaper than Class A amplifiers. And they're okay. They're okay. This is the stuff that you find on eBay, okay? And remember, you can't really complain to the company in China, all right? That's all I'm going to say. All right, Class AB, they mix these two together, okay? Not a good compromise, okay? Nowhere near as good as a Class A amplifier, but not too bad, okay? So it's right in the middle of these two, Class A and B, okay? Class C amplifiers, they're not very good, okay? It has high efficiency, but they're only suitable for CW and FM because they have poor linearity. So they can't distinguish on single sideband. If you try to use them on single sideband, your signal ends up going all over the place. God knows where it goes, okay? So for SSB, you want to either have Class A or a Class B, or an AB if you like for single sideband, and for everything else you can use Class C amplifiers. As you go down, they become a little cheaper, okay? That's all I know about amplifiers. Sorry, that's it. All right, cool. Tuning and driving a linear amplifier. The amplifier design is changed electronically depending on the band that you're on, okay? So you have to, if we were on an amplifier and we were at 40 meters, not only do you have to adjust your antenna tuner, but you're also going to have to adjust your amplifier. If we get bored on 40 meters and we go to 20, you have to adjust your antenna tuner and you have to adjust the amplifier to work on 20 meters. Most of them have, if you look on eBay, look under amateur radio or ham radio amplifiers, you see they have selector knobs, okay, depending on the band that you're on. Some of them say that they're automatic. Yeah, kind of, maybe, you know, not really. So you have to change the parameters of the amplifier depending on the band that you're on, okay? And there's a load control and a tune control and blah, 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 okay? They emit quite a bit of heat, okay? And you got to be careful when you plug your radio into them that you do it the right way, okay? And the right way is, so if we have, come on. All right, so we have our radio here, all right? And even a radio that's rated for 5 watts, like my 817, my Yaesu 817, love that radio. 817, 5 watts, and I'm transmitting. Now I want to hook up an amplifier, my amp, okay? My amp, let's say is 100 watts. They have them on eBay, I think 60 watts, 50 or 60 watts. Let's say a 50 watt, right? I cannot use it this way directly because the input of the amp has to be much, much lower. I have to take this radio and bring it down to 1 watt. Feed that into the amplifier. If I feed a full 5 watts into the amplifier, I will destroy the radio because the SWR goes off the wall as soon as you hook up an amp. The SWR goes up to 3 to 1, 4 to 1, 20 to 1, 60 to 1. You got to be careful with them, okay? Just as a word of caution. So if you guys decide that amplifier is the way you want to go, okay, be careful with that. Okay.
So
yes.
A practical question.
Yes.
Some of these cheaper SWR meters that I'm finding on eBay, like they're like 15, 20 bucks. Are they reasonably usable for? Yeah, they're fine. Okay. They're fine. Yeah. As a matter of fact, I have an SWR meter that's 20 years old. It works just fine. It's actually a very simple device. So yeah, pretty much any of them will work fine. Yeah, and okay.
it gives you a good idea. Yeah.
I want to spend $300 on an SWR.
No way. All right, neutralization. Whenever you use any kind of amplifier, you run that risk of, you know what I'm talking about, right? Start squelching and feeding back and all sorts of mumbo jumbo stuff. Okay. Most radios have neutralization, and so when you hook it up through an amplifier and you hit the transmit, it can actually become self-oscillating, and you get that hello, that kind of stuff.
So neutralization is normally handled by radios. Most upper end radios, not QRP. Well, I shouldn't even say that. Most radios of any kind of quality, actually all the ones I know of, have a neutralization circuit in it. So if it detects that it's getting reflected signal back of your output, it's being reflected back into the radio, it'll try its best to neutralize that, so we eliminate that feedback. Okay. Receiver structure. Let's see where we are. Why don't we call it quits for today? I'm getting tired, and it's been a long day, and I don't want to work your brain off. So we're going to end here at 5.4. We're going to go into heterodyne and superheterodyne. It's really nothing more than John's mixer again, okay, and the ability for us to weed out the signal. And the reason I want to end it here is I want to have a demonstration for you, which I forgot to load, and we're going to use software-defined radio to talk about receiving structures. So if you guys could finish up chapter 5 for me, okay? Not so bad, right? So it wasn't so difficult after all. I don't want you to freak over this stuff. So if you can finish up chapters 5, and then over the weekend, 6 and 7, I hope to finish them by next Tuesday. Thursday, we'll finish the last chapter, and we'll start taking some practice exams. Where I do want you to go, please, if you would, is I want you to go to www.hamstudy.org, okay? It's this site here. I'll send you the link, okay? And I want you to start taking some practice exams for the general, all right? Especially the ones I want you to deal with is the math ones. The reason I want you to deal with the math ones is there aren't that many questions. Keep doing them until you know the answers by heart, so we get past the math part, okay? So
That's a great site. That really is.
yeah, it really is.
Yeah.
And if you're not familiar with it, okay, if you take a flashcard, for example, or an exam, okay, and you don't know the answer to it, all right, just click I don't know, and it'll give you the answer. In the upper right-hand corner, you can flip back and forth between the question and the answer, and it explains the answer in detail.
And that's all the current questions?
Yes, yes. And again, under the flashcards, you can take all the ones, and the ones I want you to take are G4, okay?
G4.
And then you can go through them and make sure you, basically what I'm telling you to do is memorize the answers. It's really very simple, okay? Because I don't want you stressing and looking for calculators and that kind of stuff and rattling your cage on the exam. Everything else is pretty simple. Actually, your technician's exam was harder than your general, okay? Really, it really was. Because everything that you're learning here is just a little bit greater depth than your technical, okay? But your technical has much more voluminous amounts of information.
Question.
So hamstudy.org. I'm sorry, was there a question?
Yeah, Joe, did you send the link to the YouTube video on how to use a multimeter? If so, I did.
Did everybody get that? Did everybody get that?
Okay, I'll have to go through my emails.
Well, no, I'm just want to confirm. Did I send that to everybody?
Yes.
I believe I did.
Last week.
Yeah. If you don't get it, just send me an email. I'll send it back to you. Did you guys enjoy that video? It's pretty simple, right? Pretty simple, pretty straightforward. Yeah. I mean, I don't want you to, if we have time at the end of this, I'll be glad to go over whatever you guys are interested in, whether it's soldering or multimeter operation or oscilloscope, whatever you guys want to do. It's fine with me. If, we have until the end of the month, and we're ahead of schedule, which is awesome. And you guys have been great, absolutely great. Whatever you guys want to do, if you want to go over something in more detail, or you want to go to a slightly different area, like multimeter use or whatever, I'll be glad to go over that with you. Any questions, send them over to me. Email, don't be afraid. If you don't understand something, there's nothing to worry about. I'll be glad to go over any part of this stuff with you in person, on one-to-one. We can set up a schedule and I can help you with it. All right?
Great.
Thanks very much, guys. Have a good weekend, And
you.
I'll see you on Tuesday. Thank you.
All right, thank you.
Okay.
You're
Good night.
welcome.
Good night.
Good night.
Thank you, Joe. You're the best.
You're very welcome. Thank you so much.